Hi there. So today I want to talk to you about superhydrophobic coatings. And here you see an image of a superhydrophobic coating that's put out by Ultratech International, and it shows some dye beading up on top of the coating. So remember, in the last lecture we covered the ideas of hydrophobic versus hydrophilic surfaces. Remember, hydrophobic means water-fearing and hydrophilic means water-loving. So what you've got in these situations, usually hydrophobic surfaces are classified as having a water contact angle that's greater than 90 degrees. And hydrophilic surfaces are usually characterized by having water contact angles of less than 90 degrees. Now, what I want to talk about today, though, because we covered the regular old hydrophobic, hydrophilic in the last lecture with the Young's equation, is today I want to talk about superhydrophobic surfaces, because it's in these categories that we really have some of the applications that we see in nanoscience and nanotechnology. Alright, so superhydrophobic surfaces are highly hydrophobic, and they have water contact angles exceeding 150 degrees. And this is also sometimes referred to as the lotus effect, after the superhydrophobic leaves of the lotus plant that exhibit this characteristic naturally. In 1936, Wendells actually published a famous paper that gives a modification to the Young equation for contact angles, and it describes how a rough surface affects wetting. Now remember, your Young's equation is gamma Lg times the cosine of the contact angle plus gamma SL is equal to gamma Sg, where the gammas stand for the surface energies or surface tensions in question. So Wendells determined that when the liquid is in intimate contact with a microstructured or very rough surface, that your contact angle theta will actually change to a new value, which we'll call theta star here. And it equals cosine of theta star is equal to r times the regular cosine of the contact angle, r cosine theta. Now r here is a variable that gives you the ratio of the actual area of your surface to the projected area of the surface. So, for example, if you were looking straight on at a circle, the apparent area would be, say, pi r squared. But if it has a lot of microstructure to it, it could be a lot rougher. And that means that the true area could be much, much greater than pi times the radius of that apparent circle squared. Okay? Now, Wendells' equation shows that microstructuring a surface actually amplifies the natural tendency of that surface. So if you have a hydrophobic surface, one that has an original contact angle greater than 90 degrees, it's going to become more hydrophobic when it's microstructured. However, if you have a hydrophilic surface, one that has an original contact angle less than 90 degrees, it's going to become more hydrophilic when it's microstructured. So for example, if I initially had a contact angle of 100 degrees and the true area was 3 times rougher than the apparent area, then my new contact angle would be 121 degrees. Whereas if I had initially a contact angle of 75 degrees with the same ratio r equal to 3, then my new contact angle would be 39 degrees, much reduced. Okay, another class is the Cassie Baxter equation, and is described by this situation. Now, in 1944, Cassie and Baxter found that if the liquid is suspended on the tops of the microstructures and doesn't sink down in between the microstructures, then you're going to get an even different contact angle, which we'll call theta CB. Now, the cosine of theta CB is equal to phi times the cosine of theta plus 1 and then minus 1. Now, phi here is the area fraction of the solid that touches the liquid, okay? So what he means by that, what we mean by that, is that if you look at the little cartoon down here at the bottom, you can see that the water droplet is actually sitting on top of the pillars, and that in between the pillars, you kind of have just a suspension, right? It's sitting on air, in other words. It's resting on a little cushion of air that occurs in between the pillars. Okay, so phi is that area fraction of the solid that touches the liquid. And liquid in the Cassie Baxter state is actually much more mobile than in the Wendells state. So if you have something that's hydrophobic naturally, and then you put it in the Wendells state, the contact angle might increase even more. But if you put it in the Cassie Baxter state, it'll increase even more than that. So, for an example, if I had an initial contact angle for a system on a flat surface that was 100 degrees, but then I moved to a Cassie Baxter system with the microstructure and the nanostructure, where the liquid only touched 10% of the apparent area, then what I would have is a new contact angle of 156 degrees, so it would be greatly increased. Now, oftentimes people tried to structure these things, and they made these little pillars and designed things once we gained the capability to do that, and we could get things in the Cassie Baxter state for a while. But then eventually something would happen and the liquid would drop down in between the pillars, and we'd be back in the Wendells state again, and the contact angle would reduce. That stopped happening once we learned about hierarchical structures. Now, hierarchical structures have a microscale roughness that's actually covered with a nanoscale roughness. And these structures have very high contact angles and good stability so that they don't collapse from the Cassie Baxter back to the Wendells state. So you can see here, here's your nanostructure, your microstructure, and your hierarchical structure here. Now, the lotus leaf is actually a naturally occurring hierarchical structure. Remember that in a lotus leaf, you have your leaf covered by waxy structures. And a few years ago, some people took some scanning electron microscope images of these leaves, and you can see what they saw right here. There's these little bumps, and then on top of the little bumps are what look like little tiny waxy hairs. Okay, so that's our hierarchical structure. You have the microscale bumps. You can see the scale bar here is at about 10 microns, so that's about, say, the diameter of one of these bumps. And then you can see all these tiny little nanoscale structures on top of the microscale bump. What that causes is it causes the water to bead up on top of the lotus leaf, like is shown in the little image right there. Now, many plants, excuse me, have structures such as these. And then what happens is water, when it falls in the form of rain or when it splashes up from the pond or river that it's in or whatever, it beads up on the surface. And when that happens, any dirt or mud or grit or whatever that happens to be on the top of the leaf actually gets picked up and carried with the water as the water rolls across the surface. So it cleans the surface of the plant. Now, this gives the plant an advantage in many situations. For example, if it lives in tropical conditions where it rains a lot and is cloudy, maybe it gets splashed a lot of mud and dirt on the leaves. This gives the plant an advantage. It frees up the surface of that leaf so that sunlight can reach the surface of the leaf and not get blocked by the dirt, and it helps the plant out making energy from photosynthesis. So the lotus effect is basically the self-cleaning effect that you get because you have this Cassie Baxter condition of the nanostructure on top of the microstructure. The surface effectively traps air under the water droplets, and that makes the surface exceptionally slippery and allows for the rolling motion of the water drops across the top. This rolling mechanism is much more effective at self-cleaning the surface when compared to sliding. The slide angle is the angle at which you can tilt the surface before the water droplet will start to slide or roll. And if a surface has a very high contact angle and a Cassie Baxter type wetting mechanism, it'll be more likely to have a little tiny slide angle, which helps clean the dirt off. And here's a little schematic diagram that illustrates that concept. It shows the cleaning mechanism for a water drop sliding on a smooth surface at left, where the sliding action of the drop is inefficient at picking up particles, and on a rough surface on the right, where the rolling motion of the ball actually allows dirt to become concentrated on the edges of the drop and then get carried away more efficiently. So if you've never seen it, underneath this online lecture, I've actually posted a link to an external video on YouTube. And it demos the Leidenfrost effect. You might remember the Leidenfrost effect. If you put water on a hot skillet, basically what happens is that the water rolls around on top of the surface. And it does that because there's a little cushion of air in between the surface and the drop because it's boiling away rapidly. Liquid nitrogen does the same thing if you pour it on a room temperature surface. So what you can do is you can use liquid nitrogen to sort of dust your floor if you can afford to do that, because sometimes liquid nitrogen can be expensive. But if you have the spare liquid nitrogen, you can give it a try, and you'll see that it picks up the dirt quite efficiently, as is demonstrated in that YouTube video. And here's a little snapshot from that video, and you can see this little puddle of liquid nitrogen that's rolled around on the floor, and it's rapidly boiling away, but it's got a ton of dirt inside that little pile. Okay, but back to superhydrophobic coatings. You can manufacture superhydrophobic coatings too. It's not just something that occurs in nature. People have actually learned to mimic nature to a certain extent and create commercial superhydrophobic coatings. So there's following known possible bases for coatings that are commercially available or available right now. You can use manganese oxide and polystyrene nanocomposites. You can use zinc oxide and polystyrene nanocomposites. You can use precipitated calcium carbonate. You can use carbon nanostructures, or you can use a nanocoating based on silica. And there's a lot others out there right now. So this was a fun one that I found on the internet. This guy actually did a little TED Talk that I'm going to put as a link to underneath. And this is a commercial product called Ultra EverDry, which is a pretty awesome name. And they show great things in their videos, like guys wearing clothing coated with their Ultra EverDry, and then they throw mud on both guys. One's got the coating and one doesn't. And the guy with the coating is just still, immaculately clean after he's been tossed mud on. It's really fun. You should watch it. Now, in terms of the commercially available coatings, the silica-based coatings are actually probably the simplest to use. They're usually gel-based, and they can be easily applied either by dipping the object into the gel or via an aerosol spray. The oxide polystyrene composites are more durable than the gel-based coatings. However, the process of applying the coating can be more involved and costly. And you can also use carbon nanotubes, but those, of course, are super expensive. Thus, the silica-based gels remain the most economically viable option at present, and you can buy some of them in spray cans, as I've shown here. All right, so this guy right here is a paper that I'd like to take a minute and talk about. And it's titled Superhydrophobic Polymer Films via Aerosol-Assisted Deposition, Taking a Leaf Out of Nature's Book. Pun entirely intended there, I think, referring to the lotus leaf effect. So what they did in this paper, and here's some images from the paper here. They used the polymers Silgard, Dyneon, and NuSil, okay? And these are two-part silicone elastomers comprised of a 10-to-1 ratio of a silicon base and a curing agent. And also Dyneon is a carbon-based fluoroelastomer, which has no curing agent. And then they tested another one, two-part elastomer with a silicone base. That was a NuSil Med, and tested all of those. Okay, so basically what all of these coatings did was they generated rough surfaces that were super hydrophobic to water droplets. And the main components were the bit itself and then the curing component. And you can see some SEM images of the things. So here, top left is the Dyneon, the Silgard is top right, and on the bottom it's a deposition of the NuSil at a temperature of 420 degrees, and then the contact angle. So you can see we've got our microstructures with the nanostructures on the top in these images, and that is sort of the Cassie Baxter kind of regime, kind of range. Now what they found was that the silicone films with the curing agents and at higher temperatures had a higher contact angle, and they attributed that to an increased surface roughness. And the combination of the aerosol deposition, the curing agent, and higher temperatures allowed the films to form a network of little interconnected balls that had the higher surface roughness. And in a previous study, they dip coated with similar films and compared it to the aerosol deposition, and the aerosol deposition worked way better. However, the films do eventually wear away under scratch and adhesion test, and they're not transparent. Okay, so here in this table it lists some of the contact angles. Here they were using CA to abbreviate contact angle. And you can see if you go back to the slide what they mean about the little balls. And I bet that did come from the aerosol deposition. So if you think about it, when you spray something out, little droplets form within the air, which then hit the surface and still remain in little circles as they dry and harden. And so that probably helped. Okay, another study looked at highly transparent superhydrophobic organic inorganic nanocoatings from the aggregation of silica nanoparticles. Now, I'm going to quote them here. Normally, it is difficult to obtain surfaces simultaneously possessing superhydrophobicity and transparency. And this is because the transparency and the surface roughness are often competitive properties. So to obtain superhydrophobic surfaces, the surface roughness is necessary, but surface roughness also induces light scattering when the light falls on the surfaces. And in order to minimize the scattering, the surface roughness has to be reduced below the wavelength of the incident light. Now that's actually not too easy to achieve. So what these people did was they used nanocoatings that came from the aggregation of nanoparticles. So if you think about it, you have a nanoparticle, it already has nanometer dimensions, and then if you can force them to clump together, then you've got these balls all touching, okay, on the nanometer scale, okay? So they did that. They explained how they did it, and they could switch it from a superhydrophobic to a superhydrophilic coating after heat treating it, which is a pretty useful technique. And here they're saying that the aggregation of the particles affects how hydrophobic it is. If you switch from silica sol to a different sol, for example, a solvent, then with the addition, it's going to act as an aggregating agent, and that causes the contact angle to increase even further. So you can see here how the nanoparticles kind of balled up and aggregated, giving that hierarchical structure that's necessary for really high contact angles. And you can see they did AFM measurements of these surfaces, and you can see the surface roughness increased quite a bit because of the aggregation of the nanoparticles. And you can see here that they kept the films transparent, so the plan actually worked. And you can imagine why this would be super useful. I can't even tell you how many times personally I've dropped my phone in the toilet, but it's more than one. All right, so to summarize, there's a lot of spray-on superhydrophobic products out there, and it's still an area of current research to work on this stuff. And they work by creating a micro or nano-sized structure on the surface, and that has roughness, a high roughness, which has super water-repelling properties. However, sometimes these tiny structures are pretty delicate. I mean, if you think about it, they're made of things like silica and polymers, and so they're very easily damaged by wear, cleaning, or friction. If the structure is damaged even slightly, of course, if it's mushed down, it's really the structure of the surface that gives it that superhydrophobic property. So if you mush it or scratch it, your superhydrophobic properties are lost. So still an area of hot research and current work, so stay tuned for more. All right, thank you for your attention, and let me know if you have any questions, and I'll see you later.